All right. 2003. So we've got propane, propanone, and 1 propanol. Awesome. And then you're given the formulas. You're giving the heat of vaporization in kilojoules per mole. Good stuff. We like that. Using the information in the table above, answer the following questions about organic compounds. Ooh. So that's what I like about these questions. Back in the day when I was at Avon, the kids would always come in and say, they gave us organic questions. No, they didn't. They gave you atomic theory questions. So don't freak out and go, oh my God, it's organic chemistry. No, it is, but it isn't. So for propanone, says draw the complete structural formula showing all of the atoms and bonds. Now, again, back in the day, they did expect you to be able to do this. However, I'll give you the skeleton. So we have, yep. So C, H, 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 C, O, C, H, H. So that is, yes, that is the skeleton. So I want you to complete it. So I'll lock the screen for a second. And as always,
hi, Mr. Craig.
You follow the formal charges, and hopefully you drew it that looks something like this. That is what I did, Mr. Craig. Attaboy. So there should be 2 shared pairs, 2 lone pairs on the oxygen, and of course, all the carbons have 4 shared pairs, no lone pairs. Okay. And then double I says, predict the approximate carbon to carbon to carbon bond angle. Carbon to carbon to carbon bond angle. So we want to know, what is this? I'll give you a hint. What is the shape around the central atom, carbon? Trigonal planar. Therefore, the bond angle is 120. You were correct. Okay. All right. Oh, that was tough. All right. For letter B, for each pair of compounds below, explain why they do not have the same value for their standard heat of vaporization. You must include specific information about both compounds in each pair. So propane and propanone. So propane, probably wouldn't be a bad idea to draw that out. So propane looks like this. Whoop. C. So looking at these 2 structures, I think I have the correct ones. Propane and propanone. Yep. Okay. First of all, why is the heat of vaporization higher for the propanone than the propane? What was that? I heard something, but it kind of mumbled off into nothing. Okay. Well, let's do this. For the propanone, the first, is this polar or nonpolar? Polar. Is the propane polar or nonpolar? Nonpolar. How do we know that this is polar? Kinda. Actually, if we were to draw a skeletal structure of this, we would have, let's see here. Yeah. So we'd have the carbon, 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 and then oxygen up here with the hydrogens here, here. So I like the argument of different external atoms. Okay. But also, we just said that this is a trigonal planar shape. So even though we look at it on the two-dimensional where it looks like everybody's in a straight line here, they are not in a straight line. So when the first question asked you about the bond angle between the carbon, 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 they wanted you to start thinking about this shape right here. Okay. Even though that oxygen's kind of nestled in nicely, it is a trigonal planar shape or structure. So that's why it's polar. Okay. Careful. So we have polar and nonpolar. So let's keep going. What kind of bonding does the propanone, the top one, have? Kind of bonding. Dipole, dipole. Would anybody say hydrogen bonding? No. Why? It's where you have a hydrogen that's actually bound to an oxygen, nitrogen, or fluorine. Now, even though it's in the molecule, still doesn't qualify. Also, keep in mind that we are talking about bonds between molecules. We're not talking about bonds between atoms here. Also, what type of intermolecular force does propane have? What is it? No, I'm talking what type of intermolecular force does this compound here have? It's a nonpolar compound. It's London dispersion. Good. Okay. So there's only one type of intermolecular force between nonpolar molecules. That's why you always want to draw out the Lewis structure, determine if it's polar or nonpolar. Doesn't mean it's the weakest intermolecular force, but it is definitely weaker than the dipole-dipole because these things have similar masses. Okay. So what would account for the heat of vaporization being higher than for the propane? Very good. So we are talking about the intermolecular forces. This is an intermolecular force question. So the dipole-dipole intermolecular forces are stronger than the dispersion forces between these two structures. Therefore, the propanone will have a higher heat of vaporization. Okay. All right, between the propanone and the 1-propanol. So probably not a bad idea to draw this out. Let's see if I can find some room to do that. Actually, I'll do it over here. So 1, 2, gotcha. Let's go tiny here. Carbon, carbon. Is there 3 carbons? Thought there were 3. Yep, 3. Carbon, oxygen, hydrogen. Oh, wait. And then go ahead and put your dots in. Is that drawing as accurate as it can be, according to formal charges? Yes? No?
Yes.
Excellent. Yes, it is. Uh-oh. Okay. So we have this compound versus this compound. So what is this polar or non-polar? Polar. Good.
Polar.
What type of intermolecular forces do we have? Hydrogen. Very good. Now, later on, that's where the reason why for the hydrogen bonding. Okay. I'm not so concerned about it this week as I am in April, but there is another intermolecular force that is associated with this compound. Anybody guess? What is it? Say what you said. Say it. Oh, no. Thought I heard something else. What do you think is happening if I had neighboring molecules with all these hydrogens here? What is it? Now, your options are hydrogen bonding, dipole-dipole, or dispersion. Dispersion, very good. And you're going to find, as we speak in April, that we can have, actually, I'll turn the camera on so Con can see what I'm doing. God, she's in bed. Awesome. Make yourself comfortable. So even though we'll pretend that my hand is like the way the molecules are. So if I have it oriented like this, maybe my hydrogen-oxygen bonding is taking place here. But if say my wrist represents the other side that has only hydrogen, once they come together here, 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 those are attracted with very weak dispersion forces. The strongest one occurs between the hydrogen and oxygen. However, there is dispersion, and dispersion, so to speak. I know that's kind of dang it. Kind of simplistic. Yeah, boy, what'd I do? Daggone it. So it seems kind of simplistic, but the reality is when you look at all the molecules, they'll have their strongest intermolecular force, which in this case is due to the hydrogen bonding, but also you have the dispersion. Again, I'm not going to count off if you don't talk about dispersion this week. In April, I will drill you to no other and say that everything has a dispersion force plus its strongest one. Okay. So in case you're like, I don't know, the key says that it has dispersion forces. Because again, when it repositions itself in a weird way. Okay. Say it again. That's not AP. We're not talking about that. All right. Letter C. Draw the complete structural formula for an isomer, the molecule you drew in AI. Oh, this is a great time to talk about isomers. Does anybody know what an isomer is? Not everybody at once. Yes or no? Do you know what an isomer is? Okay. So an isomer is a different structural setup with the same chemical formula. So later on in organic, you will call this carbon. Whoop, let's make that a little thicker. You will call this the number 1 carbon, the number 2 carbon, the number 3 carbon. And in reality, the number 1 and number 3 carbon in this drawing happen to be the same thing in terms of reference. In other words, if I take it and spin it, there's no difference. Isomers mean that we can have a different shape, but the same formula. So since we have one thing that's here, let me erase this so I have room. So I can, if I have my carbons situated, as they are carbon, 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 I can now have hydrogen here, which doesn't change anything, but I can move this oxygen to over here. So now I've got hydrogen, 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 hydrogen. So it kind of looks similar to what we did in the previous, but this has one less hydrogen. And notice that if I look at my carbon, 1, 2, 3, now we are very definitive in what the number 1 carbon is, the number 2 carbon, and number 3. So an isomer, if we were to draw this correctly, yep. Hang on here. So hydrogen, I have 6 on the top. Oh, that's right, because I do have too many bonds here. Hang on. Sorry. Yep, that's true. My bad. My bad. My bad. So we have 6 there. Wait a minute. True. Because it wants 2 shared pairs. There we go. Better? All right, so an isomer, and again, we'll talk a lot more about that later on, is that we are simply moving the functional group around. Again, you don't have to know what functional groups are, but this is considered a ketone. Don't need to know that. All you need to know is the oxygen has moved its location. Okay? So different shape, same formula. Oh, yeah. Letter D. Given the structural formula for propanone, and the INE at the end here means that we have a triple bond. And I'll give you another little hint here. That if you have an ane, that means they're all single bonds. They don't have an ene in here, but the ENE means that you have a double bond somewhere. So we don't have any of the enes, but we do have an ine here. Okay? So the question wants to know, given the structural formula for the propanone below, indicate the hybridization. So what is the hybridization on the carbon indicated? What is the hybridization on the carbon indicated? Duffer, this one's on you. What is the hybridization for the carbon indicated? I love this question.
Is that like the SP?
I don't know. Throw something out.
It's either, I don't know if it's a sigma pi thing or that.
Give me one answer. SP3? Does everybody agree? Uh-oh. SP... SP... Woodard? It's just SP. Because what is the shape here? A line. In other words, how many external atoms on that central carbon? 2. So how many letters should you have? 2. So it's just SP. Okay. Now Duffer's ready for the next part. It says indicate the number of sigma and pi bonds on the whole thing. All right, Duffer, this is your chance to redeem yourself, girl. Yowza. That's fun. Okay, let's see here. So 1, 2, 3, 4, 5, 6. And pi? Awesome. And on the exam, part double I would be worth 2 points. Okay. All right. Questions on this one? What a fun one. Woo. All right, the last one. 1980. Oof. I was in junior high. I know. Write the ground state electron configuration for arsenic, showing the number of electrons in each subshell. So in other words, draw arrows. I'll let you do that.
Oh, found it.
So first of all, you got to know what arsenic is. So that's AR, right?
No.
Just checking.
Ah, why does it take so long?
Mr. Craig, where is this?
Huh?
Where is this?
It's the more review on the schedule.
Oh,
On the proposed schedule?
Yeah, day.
it's all together in the big
11,
file.
November 11th. It says
What do you mean the big file? I can
Yeah, I never get to this.
it's like at the top, like they click
Oh,
this
boy.
on the PDF,
Oh,
and then it's like everything.
Oh.
I don't do
No
that.
idea that was there.
Mr. Craig, you're like, can you do a short one?
No.
What?
It doesn't say to do the short. It didn't say do the shortcut one, did it? I guess Eric's not in the game of. It could be. It could be. You. It's all right. Yeah, I'll show later.
It's not open.
What's not?
There we go. I think that's good. Oh. Ow.
And. All right. Showing the number of electrons in each subshell. That's it for A. Boo, that's boring. B. Give one permissible set of 4 quantum numbers for each of the outermost electrons in a single arsenic atom. Ooh. Whoa. Give one permissible set of 4 quantum numbers for each of the outermost electrons in a single arsenic atom. Okay. So let's start off with the 4s electron. The first quantum number would be what energy level are we in? 4. First one would be 4. Good Lord.
are we doing 4S?
Because it says for each permissible, where is it here? Outermost electrons. So the outermost electrons are in which row? 4, the row that they're in.
Why wouldn't you do 4? Yeah, why not 4B?
We will. Don't worry, we will. Okay? So the second quantum number, what is a permissible, and again, focus on the 4s. 2? Uh-oh.
Actually, subtract 1 or something. Like 10 or something.
I'll give you a hint. You need to know the quantum numbers and what they represent before Thursday. So you might want to put that on the to-do list. So the second number, the first number represents the energy level. The second number represents the orbital. Very good. And we're looking at an s orbital. So it has a quantum number of 0. Very good. You guys suck at this. Not going to lie.
You learn in trash.
Where's the things that you're putting by
Those would be commas. Yes, it is a strange, crazy system. The third principal quantum number represents what? You guys are on a streak. You may as well keep it up. Orientation. Very nice. What's that?
Wait,
No, that's
That's
been. That's
like-
the fourth.
No, that's never mind.
that's the.
I don't know this from last year.
It's a zero.
It's 0. Its only option is 0 because how many different orientations are there for an s orbital? 1.
Yep.
So in other words, when you do it, this is n, this is m, sorry, l. This is l sub m, which again represents you go from your n minus 1 to get through 0. That's what this represents for that one. And then this guy represents L through 0 through negative L. Well, we only have 0, so that's our only option. Okay. And then, now that you guys are on a streak,
Wait, why is L 0?
because there is only one orientation. So L is 0. It goes through 0 to negative L.
I know. I'm talking about the second one. Then why is
Because 0 represents an s orbital. We're talking about an s orbital. S orbital. All right, and then plus 1/2 or minus 1/2? Yes, it could be either. Okay. Since I'm positive, I'll put that one. All right. 4p. What should the first number be? 4. Very good. Second number. 1, because that represents p orbitals. 2 represents d orbitals.
When do you do n minus 1?
Oh my God. And then what is a permissible number for the third number? Could be negative 1. Could be 1. Could be 0. Just for kicks and giggles, I'll put 1.
So it's like 1, 0.
No, it says
That's stupid.
a permissible set. Okay. So we wouldn't put the 3Ds because that's not the outermost. The fourth is the outermost. Whew, that was rough. All right. Letter C. Is an isolated arsenic atom in the ground state paramagnetic or diamagnetic? I'll give you a hint. Maybe if I can zoom in. I believe so.
Hey, in your notes it says not our responsibility to know which direction the electron spins.
What?
It says in your notes it is not the responsibility of the student to know which direction the electron spins. Just know the
Very good.
electrons in opposite
Mr. Greg, did you say you could put something before, like the S or the D into the P if you could get a half or full?
Mm.
No.
S to D only.
You can fill up D, you can't take out.
Okay, never mind.
Thank you, thank you.
Go with the die.
Dia?
Yeah.
Uh-oh.
50-50.
It was. Let's just say you're not a good gambler. How's that? Paramagnetic means that you have an orbital that doesn't have all of its electrons doubled up.
Craig, how do you know it's spin? Just answer the question.
Okay. Letter D. Good Lord. Oh, sorry. Got it. Yeah, and the explanation is because paramagnetic means that if you have an orbital with an electron, it has to have a twin or a buddy. In other words, all orbitals that occupy electrons must have a twin for it to be diamagnetic. This one has empty or half filled. Sorry.
All electrons need to be paired.
Say again.
Let's say Had one more electron.
Oh, here. I think you're saying if we had, say, one more electron and we just did this, would we be good?
No, you can do
Oh.
Very good. We cannot do that.
I'm saying
That's
that's
what
one
I'm
more.
saying. If you had one more, would it still be?
Would it still be there?
So this,
Because those two on the right.
those two on the right do not have a buddy.
Not buddy, so it's
Correct. Still para. What about now? What about now?
It can be a
Very good.
that's positive or negative. So you can choose one of it.
All right. D. Explain how the. Let's get it correct again. My bad. Since they're talking about the electron configuration, I want to make sure it's right. All right. Explain how the electron configuration of arsenic atom in its ground state is consistent with the existence of the following known compounds: sodium arsenic, arsenic or AsCl3, and AsF5. How in the world are these consistent? Consistent.
Because they all donate 3 electrons.
Consistent.
They all are arsenic in
Uh,
them.
They all have arsenic in them. Very good, boy.
Let's go. Too good.
Wow.
Too good. Is that the answer?
No, that's not an answer. That's garbage. God. My recommendation is to draw the electron configurations.
you have to do
What the hootie, hey?
it. Isn't it
What's that say?
not
What's that say? What is that word right there?
donate?
Donates. Okay. Or shares. Yeah.
Oh, is that a 5 or 3? I cannot.
The other one's a 5.
Oh, that's wrong. I don't know.
Oh.
Forgot it said it's 5.
Oh, what are these X's for?
Oh, wait. My bad.
Wait. What are you doing?
What you got?
There's one.
Hey, just click on my brain.
Oh, not nice.
In other words, what did I just draw here in case you would be asked to draw something like that on a test sometime in the near future?
Vanderwall.
God.
There's the word. There's charges up there.
Good Lord. This would be an ionic Lewis dot structure.
Whoa.
I know. Whoa. That's right. What was the other? ASCO?
Where did you get that? Yeah, one of those. Did you have a video
The
on all that?
X's are the most.
No, I'm just showing who arsenic belongs to. You're correct. It's not. But when it's asking how these things can come about, oh,
Wait, I was right. It just shows up at 5s orbital after. Aha, I was right.
Aren't they sharing
Halfway.
those?
Not 3.
Oh, yeah, they don't care about sharing.
who don't care about sharing?
Nothing.
Come on now. They do care about sharing.
They just don't want it back.
Wait. What did you say? It's on the right side of the slide, right? That's still go with it. Just stop going.
Let's clean this up a little. So, says explain how the electron configurations of arsenic in the ground state is consistent with the existence of the following known compounds. So, Alice said it well. The sodiums each bring 1 electron. Arsenic would love to have 8. It only has 5. So the 3 sodiums in combination with each other provide the 8 electrons. In AsCl3, each chlorine brings 7 electrons. And to share with the quote-unquote 3 that are available for arsenic, to allow arsenic to have 8 and chlorine to have 8.
So they each provide.
Formal charges is good. I like that. Heck yeah. And then the same thing with the fluorines.
That won't be on the test vote.
Why not?